Hi again, Calc BC. Welcome back. So we finished up all of our review of our differentiation formulas. You have all 22 of those in the front cover of your book. They should be pretty much right up here by now too. I know it's been a while since you did them, but you did do them a lot last year as well. Now we're going to take a trip through and look at some applications of derivatives. The first couple are pretty straightforward, I think, related rates and uh, optimization problems, and then we'll do some curve sketching and kind of get through our work here in derivatives, hopefully by the end of the month, maybe beginning of November, so that we can transition over and start looking at our integration, where we'll spend a little bit more time just because there are a few new things in there as well. Along the way, we'll hit some ideas in derivative calculus that ones that you probably remember, but maybe have could use a little refresher on. So we'll start off with the idea of an implicit derivative. So this comes to us because the functions we've been dealing with have been primarily explicit. Stuff like y equals the square root of x, okay, or y equals the sine of x. Something like that, okay? Where it's very obvious, like y is dependent upon x. But in an implicit function, we don't always have that. We get stuff like, like 0 equals x squared minus y. Now it's an implicit function. Like we don't really know which one's depending on which. Or, 0 is equal to arc sine of y. Don't know what's going on my computer right there. Arc sine of y minus x, right? And so now we're talking about a totally different kind of animal. And so just a reminder that there's a really nice little table on page 138. Not a table, it's a gray box, right? One of Dr. Larson's sort of infamous gray boxes on page 130. It has the guidelines for implicitly deriving things. So I'm not going to spend a whole lot of time reviewing it because I know we did a lot of it last year, but I thought it would be worth going through an example just to quickly remind everybody. You take a derivative in a case like this, and we want to say maybe find the slope of the tangent line to this graph. Now this is a lemniscate that loops over itself. So the derivative is actually going to be dependent on both x and y, because not only does it matter where you are horizontally, it's also going to matter where you are vertically on the graph. And so when I go to start my derivative here, I'm just going to remember that slope is dy over dx. So I'm taking my derivative with respect to x. Now, to start off with, I have this constant 3 here. I'm just going to kind of keep that guy out of the way here. And I'll just start by deriving this function inside here. Now, we do have a chain rule here. We bring down the 2, and then we have x squared plus y squared to the first power. Then you're going to multiply by the derivative of the inside function. And this is where the implicit derivative kicks in. Derivative of x squared with respect to x is simply 2x. But the derivative of y squared with respect to x, right? Well, that's then treated as if it's a chain rule problem. The implied function is that y is actually implied to be some function of x. So we bring down the power, subtract 1 from the power. Now we multiply by the derivative of the inside function. The derivative of y, I'm just going to use Newton's notation here, is y prime. And so that's how we would get our derivative on our left-hand side. Over here on the right-hand side, of course, we have a constant of 100. And now we have x times y. Don't forget the product rule. So many first years look at that and go, oh, great, x, y, that derivative is easy. Derivative of x is 1, derivative of y is y prime. This is 100y prime. No, it's not. It's a derivative of x, which is 1 times y, plus x times the derivative of y, which is y prime. So many first years forget when they're driving the, well, okay. First thing, a lot of first years, they forget to drive the right side at all. Okay, that happens. Yeah. Some of you might have done that last year when you were early on at this. And then they just forget that that's a product. It's like they've never seen the product rule before, and all of a sudden their mind starts playing tricks on them, right? But not us. We're going to be better than that. So now it's just a matter of figuring out what does dy dx actually equal to. So I'm going to do a little bit of the algebra here. On this left side, you can see it's actually a binomial times a binomial here. We've got 2x squared plus y squared times 2x, and then we've got 2x squared plus y squared times 2y prime equals 100y plus 100xy prime. So now you can see I've got this, well, let's bring the 3 in, I guess, right? Might as well, because we're going to have to move a bunch of stuff around anyway. So now I've got 12x times x squared plus y squared plus, let's see, oh, look, there's a 12 there as well. So I've got a 12, well, 12y, and I've got an x squared plus y squared y prime is 100y plus 100 x y prime. So now we just got to get all the stuff with y prime on one side and all the stuff without a y prime on the other side. So I chose to go this route, 12y x squared plus y squared y prime minus 100x y prime equals 100y minus 12x times x squared plus y squared, like so. And now you can see all the stuff with y prime is isolated on the left-hand side. So we can just factor out the y prime. Y prime times. So now we have 12y times x squared plus y squared minus 100x equals 100y minus 12x x squared plus y squared. And you just divide by the factor that doesn't have the y prime in it. And we end up with 12y times x squared plus y squared, did I get that? Yeah, minus 100x. And that's what y prime is equal to. And like I said, you know, this one's got a lot of algebra to it, but you know, it's not it's not overly complicated in terms of the process here. If you're thinking, hey, look, there's a 4 in common in there, that's a good thought. I just noticed I got 100y and 12x x squared y squared on the top, and 12y x squared y squared minus 100x there. So yeah, we could reduce that by factoring out a 4, top and bottom, and canceling that out. So I guess that'd be 25y minus 3x times x squared plus y squared over 3y times x squared plus y squared minus 25x. But yeah, so that's a quick refresher. You know, implicit derivatives. Just remember that it means we're deriving with respect to a variable that may or may not even be in the function, and that's what kind of spooked people, I think, initially about related rates. Was, you know, this is where we're going to apply finding an implicit derivative. But we do so when, you know, the derivative is done with respect to time, and time might not necessarily be how we related the rates in the first place. Okay, so remember, with related rates, you know, it always comes down to just a couple of different relationships, right? Do you remember what they are? Maybe you do. But yeah, you know, how many times did you see a related rate problem come down to the Pythagorean theorem, right? I mean, it comes down to that all the time, right? Because, you know, that's the distance formula, right? That's what it is so much of the time. Or how many times did it come down to the volume of some sort of known geometric figure, right? Or the area of some known geometric figure. Yeah, you know, like we had the one where it was like the spherical ripples of water in the pond, right? Cool, totally calm water. We dropped a pebble in and watched this concentric circles go out, and we were like, oh, what's the rate of change of the area of the disturbed water if the radius is changing at 2 feet per second or whatever it is, right? Yeah, it came down to some known geometric figure. What else did it happen to be? Well, oh yeah, how about trig, right? It was either so, ka, or toa. Oops. Yeah, there was some you know, triangle, right? And we were trying to find the rate of change of one of the angles in the triangle. You know, I mean, that happened all the time in these things, you know, and those are, those are pretty much it, right? I mean, all related rate problems, it always comes down to those things. I guess, okay, there's one more. I almost forgot. Everybody's favorite, right? Shadow Man, right? How did you solve the Shadow Man problem, right? Similar triangles, of course. Yeah, so we know that these are the main ways that we relate to quantities. Now, there may be some weird ones out there that have some other sort of strange relationship in them, but for the most part, any related rate problem comes down to one of these four things. How about the quintessential related rate problem? There's a couple of them, right? How about ladder sliding down a wall? That's always in there, right? It's just got to be there. It's in every single calc book out there. So we have a house and we have a ladder leaning up against the house. Okay, here we go. There's our ladder, and your ladder. Oops, it's got to be on the ground there. Your ladder is let's say 5 meters long. Oh, let's do it in feet. Feet's got some more fun with it, because then we can say it's a 25-foot ladder. And then we can say, look, the ladder is out from the wall. How far? Right? Usually is it 7 feet? Because then there's the classic the 7, 24, 25 Pythagorean triple, right? And so then the problem always goes something like this. So your buddy thinks it'd be really funny to take the base of the ladder right here at this point and move it away from the wall. Let's see, do I have one handy in here? I'm sure I've got a ladder problem in here somewhere. It's in every calc book. Oh, there it is. And it looks like they're going to move the ladder away from the wall like 2 feet per second, right? Okay, and so we set up our relationship between the rates of change of the sides of the triangle, right? Well, the good news is in this case, let's say the 25 is constant, right? Not changing. Okay, but the 7 and the 24 are. And so just a reminder that what that means is you want to label these with some names, right? Because they are changing. If you put in a number for them, then you've sort of frozen them in time, right? And we don't want to do that because they're changing. So we always put in variables until after we find our derivative, stuff you already know. Okay, and what was the key relationship here? Maybe we're trying to find the rate of change at which the ladder is sliding down the house. In other words, we want to find dB dt. Okay, well, obviously this is the first one, Pythagorean theorem, right? You all knew that already. So we're just going to say a squared plus b squared equals c squared. And because the 25 is constant, we can actually substitute that in there and say a squared plus b squared equals 25 squared. We can do that before we derive because it is a constant. Now we're ready to derive. And of course, 2a, but then remember, we're taking the rate of change with respect to time, so it's an implicit derivative there. So that's got to be dA over dt multiplied because of the chain rule. B squared has to be 2b and then over, or dB over dt. But we do get to put in the 0, which is nice, because when you derive that constant, you get 0. And then you just plug in everything that you know. We're given everything that we need here. We know A is 7. We know dA dt is that 2, right? That's our dA dt. And as you probably remember, it is important to put in the correct sign for that. Since A is getting longer, that is a positive 2 feet per second. If A was getting shorter, we'd want to definitely put in a negative because that's going to affect the sign for B. Now we'll just plug it all in, and we're going to get 2 times 7 times 2 plus 2 times 24 times dB dt is 0. And if you're going, man, there's a lot of 2's in this thing that we could cancel out. You're right, there are. Let's go ahead and cancel out a bunch of them. So we get 7 plus 12 dB dt equals 0. And so dB dt is negative 7/12 foot per second. And there you go. So there's a quick hitter reminder of a related rate problem. Now I can do the same thing. I can have the same scenario set up and ask a different question. And so it totally changes how we approach the problem, right? This was a Pythagorean theorem one. But what if I said, oh, well, hey, I'm more interested in the rate of change of the area of the triangle that's formed. Okay, so now I'm not talking about dB dt anymore, right? No, I want to talk about the area of the triangle that we formed inside the figure, right? So it's in here, this triangle. Oh boy, that didn't go very well. I'll just kind of lightly shade it in here as best I can. Inside here, if I want to talk about the area of that triangle, well, then my equation has to change, right? Because now it's a known geometric figure. It's the area of a triangle, and the area is, of course, 1/2 base times height. So in this case, 1/2 of A times B. And then you would go through the same process. I might change the problem again. I might say, oh, well, all right, so you're able to do that one. Maybe it's the same setup, but now I want to know what's the rate of change of the angle between the house and the ladder. Angle here, let's call it theta. Now I'm asking what's the rate of change of the angle, that's d theta dt. Well, now what are we going to use? Well, we're going to use a trig ratio, right? We're going to use SOHCAHTOA, okay? I would strongly suggest you stick with probably the sign, right? Because that way it's opposite over hypotenuse, because the hypotenuse is constant, right? You could do opposite over adjacent, tangent, but then you need dA dt and you need dP dt. And well, now we know what it is. In this case, it's negative 7/12. But if you were starting from scratch, you might not know that. So there's a great example of a related rate problem. That's one of the classics. You know, the baseball player running around the diamond, that's another classic one. So the first set of homework here, guys, has some basic ones. We will come back together before we try the more complex, you know, like shadow man problem and stuff like that. And then next video, we're going to compare related rates to an optimization problem and how are they similar and how are they different. So. All right, guys, that's it. So implicit derivatives and related rates. Thanks for coming in and watching. And don't forget to post those notes, get those turned in on time. And I will see you guys in class very soon. Thanks so much, and we'll talk to you later.